Imagine for a second that you've just bought a plot of land.
Okay, a plot of land.
Yeah, prime piece of real estate.
Yeah.
And it's totally yours. You can build a fortress or a skyscraper, a massive warehouse, whatever you want.
Sounds pretty good so far.
Right. But here is the catch. This land is invisible.
Invisible.
It is floating in the digital ether. And if you don't build the right fences and the right roads and, hire the right security guards, immediately...
Anyone can walk right in.
Exactly. Anyone. Or, and this might actually be worse, you build a maze so complex that you get trapped inside and you literally can't get your own data out.
That sounds like an absolute nightmare, but honestly, it's a surprisingly accurate description of what we are talking about today.
The infamous VPC.
The VPC, yes.
So today we are staking our claim in the cloud. We are doing a deep dive into the Amazon Virtual Private Cloud.
Long overdue, I think.
Wow. Oh, absolutely. And looking at this massive stack of documentation we've got, I mean, the user guides, the security white papers, the recent pricing updates, it is very clear that the VPC is where the whole dream of the cloud just crashes into the cold, hard reality of IP addresses.
It really is. I mean, I often tell people that the VPC is the nervous system of your cloud application.
The nervous system.
Yeah, because you can have the most powerful servers and the smartest AI models in the world, but if your VPC isn't architected correctly, those servers are just expensive bricks.
Right, they can't actually do anything.
They can't talk to each other. Or worse, they are just screaming their confidential data out to the entire public internet.
Which is exactly what we do not want. So the mission for this deep dive is to move beyond the acronym SOUP.
And there are a lot of acronyms.
So many.
Yeah.
We need to understand the physics of this virtual world. How do we isolate traffic? How do we punch holes in that isolation when we actually need to? And really, why does getting this wrong cost so much money?
Exactly. We are going to turn that chaotic public cloud into a very boring, very secure private network.
I love boring and secure. So let's start with the absolute basics. When I open a brand new AWS account, what exactly is a VPC? Like, is it a piece of hardware somewhere in a server rack?
No, it's purely logical.
Purely logical.
Right. A VPC is a logically isolated virtual network dedicated to your specific AWS account.
Okay.
Think of it as a slice of the massive shared AWS pie that has been carved out just for you.
So it's my own private bubble.
Exactly. It mimics a traditional network you'd have in a physical data center, cables, routers, switches.
Yeah.
But it is all software defined.
Okay, logically isolated. I get that. Now, usually when we talk about AWS, we talk about regions, right? Like US East or London. Does my VPC span the whole world?
No, and this is constraint number one. A VPC lives entirely within a specific AWS region.
Okay, so it's geographically locked.
It cannot stretch from New York to London. It is bound to that one geographic area. But inside that region, you have to make the most critical decision of your entire setup. Subnets.
Subnets, the subdivisions of my digital land.
Right. A subnet is just a range of IP addresses. But here is where the physical reality actually checks in, and this is where a lot of people get very confused.
Okay.
A subnet must reside entirely within a single availability zone.
Let's pause there because availability zone, or AZ, that sounds like pure marketing speak. What is it really?
Right, it does sound like marketing, but an AZ is effectively a physical data center.
A real building.
A real building or a cluster of buildings with its own independent power, cooling, and networking.
Okay.
And they are physically separated from each other by miles. The idea is to prevent a disaster like a flood or a fire from taking out two of them at the exact same time.
So when you tell me a subnet can't span zones, you're saying a subnet is tied to a specific physical building?
Essentially, yes. And this is a very deliberate design choice for failure isolation.
Failure isolation.
Right. If you launch all your servers into one subnet, you are physically placing all your bets on one building. If that building loses power, your whole application goes dark.
So the strategy here isn't just make a network, it's spread your bets.
Precisely. You create multiple subnets in different availability zones. So if AZA goes down, the traffic automatically shifts over to the subnet in AZB. You are designing for failure from day one.
Now I have to ask about the default VPC. Because when I log into a fresh account, I always see a VPC already sitting there.
Yep, it's waiting for you.
I didn't build it. It has subnets. It has an internet gateway. It has everything. It feels suspiciously easy.
It is easy. It is the plug-and-play version. AWS gives every account created after, I think, December 2013 a default VPC.
Okay.
It is designed so you can launch a server, like an EC2 instance, in 30 seconds without needing to know what an IP address is.
But I sense a massive but. coming here.
A very big but. The default VPC is configured with public subnets everywhere.
Everywhere.
Everything you launch in there has a direct path to the internet.
Oh, wow.
For a quick test, it's fine. For a production database that holds actual customer data, absolutely not. Right, you want a non-default VPC, one that you build entirely from scratch.
Because in the custom one, I control the size of the network and the exposure.
Exactly.
And speaking of size, we really need to talk about CIDR blocks. This is the part of the documentation where everyone's eyes just glaze over.
Oh yeah, CIDR blocks are notoriously dry.
But you flag this in your notes as a one-way door.
It is a massive one-way door. When you create your VPC, you have to assign it an IP address range, usually using CIDR notation like 10.0.0.016.
Right, the /16.
Yes, and that number at the end, the /16, dictates exactly how many IP addresses you have. In this case, it's about 65,000.
Okay, so what if I pick a range that is too small? Say, I don't know, I pick a /24. The guide says that only gives me 256 addresses.
Then you're going to run out of space very, very quickly. And here is the kicker. You cannot change the primary CIDR block of a VPC once you've created it.
Wait, really? I can't just go into the console, hit edit, and make it bigger?
No, you absolutely cannot.
Wow.
If you build your entire empire on a tiny plot of land and you fill it up, you can't just expand the foundations outward. You have to literally build a brand new VPC, migrate all your data over, and tear the old one down.
That is complete nightmare fuel.
It is a painful, expensive mistake. I've seen companies spend months unwinding it.
Okay, so lesson 1 for the listeners. Buy a big enough plot of land. Do not be stingy with the IP addresses.
Exactly. Go big on the private range because it's free.
Okay, so we've got our land, and we've subdivided it into subnets across different physical buildings. Now we need roads. How does traffic actually know where to go?
That is the job of the route table. Every single subnet must have a route table associated with it.
So it's like a GPS.
It is exactly the GPS navigation system for your packets. Now, if you don't explicitly assign one, the subnet just uses the main route table by default.
This leads right into the confusion between public and private subnets. When I first read this, I assumed there was just a checkbox in the console, make this public.
I really wish it were that simple. No, there is no magic switch. Whether a subnet is public or private is determined entirely by its routing.
Walk me through that. What actually makes it public?
Okay. To make a subnet public, you first have to attach an internet gateway or IGW to your VPC.
Okay, the IGW.
Then in the route table for that specific subnet, you add a rule that basically says traffic destined for the internet, which is denoted as 00.000.00 goes to the IGW.
So if I add that specific route, boom, it's public.
Boom, it is public.
And if I don't?
If you do not have that route to the internet gateway, the subnet is private. The resources inside can talk to each other, but the internet cannot reach them, and they cannot reach the internet.
Which sounds absolutely great for security. I put my database in the private subnet, and it's totally safe.
Very safe.
But wait, my database eventually needs to download a security patch from the internet, right? If it is in a private subnet with no route to the outside, isn't it completely cut off?
Yes. This is the classic architectural paradox in cloud networking. You need to get out to get updates, but you do not want anyone getting in.
Right. So how do we fix it?
The solution is the NAT gateway.
NAT. That stands for Network Address Translation.
Right. You place this NAT gateway inside your public subnet. Then you tell your private subnet, hey, if you need to go out to the internet, route your traffic over to the NAT gateway.
So the NAT gateway acts like a courier.
Exactly like a courier. The private server hands the request to the NAT gateway. The NAT gateway walks out the front door through the internet gateway, gets the data, walks back in, and hands it directly to the private server.
And the key detail here is the direction of the traffic, right?
Yes, it is crucial. The NAT gateway only accepts traffic initiated from the inside.
Gotcha.
If a hacker on the public internet tries to connect to the NAT gateway to get into your database, the NAT gateway just drops the connection. It is a strict one-way street.
That is very clever. But I was digging into the pricing documentation, and this courier isn't exactly cheap, is he?
Oh, definitely not. And this is where the AWS bills start to really hurt. NAT gateways have a flat hourly charge just for existing, but they also charge a fee for every single gigabyte of data processed through them.
So if I am downloading terabytes of updates or God forbid, moving data backups through that NAT gateway.
You're going to get a very unpleasant surprise at the end of the month. I have seen startups burn thousands of dollars just on NAT gateway processing fees alone because they didn't realize every single bit of traffic going to the internet was being tolled.
That is a massive gotcha. So the road out of the fortress is a toll road.
Always a toll road.
Okay, moving from routing over to security, we have our land, we have our roads, and we have our very expensive courier. Now we need the bouncers.
The bouncers, I like that.
According to the docs, we have two main tools here: security groups and network ACLs. Let's start with security groups.
Security groups are your bread and butter. The most important thing to visualize here is that a security group wraps around the instance itself, not the subnet.
The instance, so the specific server.
Yes, it is a force field around a specific server.
So I could have two servers sitting right next to each other in the exact same subnet, but they have completely different security rules.
Exactly. One could be a web server that allows traffic on port 80, and its neighbor could be a database that only allows traffic on port 5432. They operate totally independently.
Now, the documentation uses a word that seems to be like the holy grail of VPCs. Stateful.
Yes, stateful.
What does that actually mean in plain English?
This is the biggest aha moment for understanding VPC security. Security groups are stateful. This means they have a memory.
A memory.
If your server sends a request out, say, to download an image, the security group remembers that specific request. When the response comes back, the security group automatically opens the door to let it in.
Wait, even if I don't have an inbound rule explicitly allowing it?
Correct. You do not need an inbound rule for return traffic. If the request was allowed out, the reply is automatically allowed back in. It tracks the state of the connection.
Wow, that simplifies life immensely. I don't have to worry about configuring the return trip at all.
Not at all.
What about blocking people? Can I write a rule in my security group that says, block this specific IP address?
With security groups, no. They are allow only.
Allow only.
You literally just list who is invited to the party. If you aren't on the list, you are implicitly denied. You cannot explicitly blacklist someone.
Got it. It's a very exclusive club, not a police lineup. Now, there is one feature of security groups that feels almost like magic, and you called it referencing in your notes.
Oh, I absolutely love this feature. In the old days, on physical firewalls, you would write rules using hard-coded IP addresses. Allow 192.168.1.5.
Right.
But in the cloud, IP addresses change all the time. Servers spin up, they crash, they auto-scale based on load.
Right. It's totally dynamic. If I have to update my firewall every single time a server restarts, I'm never going to sleep again.
Exactly. So instead of IPs, you use the security group ID.
Okay.
You basically tell your database security group, allow traffic from anyone wearing the web server security group badge.
So I don't care what their actual IP address is. If they flash the badge, they get in.
Exactly. You can scale your web servers from one instance up to 1,000 instances, and you never have to touch the database firewall rules once. It's dynamic trust.
That is incredibly smart. Okay, so that is layer one, the security group. Layer two is the network access control list, or NACL. How is this one different?
Well, if security groups are the bouncer at the club door checking individual IDs, NACLs are the border patrol at the city limits.
Okay.
They operate at the subnet level, not the instance level.
And are they stateful too? Do they have a memory?
No, and this is where people get into really deep trouble. NACLs are stateless. They have total amnesia.
Total amnesia, meaning they don't remember that I asked for something?
Zero memory. If you allow traffic in through a NACL, you must also explicitly write a rule to allow the return traffic out.
Okay, I mean, that sounds slightly annoying but doable. I just write two rules.
It sounds doable until you encounter something called ephemeral ports.
Ephemeral ports. This sounds highly technical, but judging by your tone, it's the thing that breaks everything.
It breaks absolutely everything if you ignore it. Here are the mechanics. When your server connects to a website, it sends a request to port 80 or 443. We all know those common ports.
Right, HTTP and HTTPS.
But your computer expects the website to reply to a completely different port on your machine. A random, high-numbered port, usually somewhere between 124 and 65535.
A random port. Why would it do that?
To distinguish that specific conversation from all the other tabs or connections you have open, it is temporary or ephemeral.
Ah,
So with a stateless NACL, if you want to allow your server to browse the internet, you can't just allow port 80 outbound. You have to also allow the return traffic on this massive range of ephemeral ports inbound.
whoa. So to make it work, I basically have to open up a huge chunk of my network border.
Yes, you end up opening ports 1024 through 6535 to the entire internet just to ensure you get a reply.
That feels really unsafe,
Mm.
or at least very broad.
It is very broad, which is why many people find NACLs to be blunt and difficult to manage compared to security groups. It is so easy to accidentally cut off your own legitimate traffic.
So why even use them? Why not just stick to the stateful smart security groups and ignore NACLs entirely?
Two main reasons. First, defense in depth. It acts as a backup net, just in case someone messes up a security group.
Okay.
Second, unlike security groups, NACLs actually allow deny rules.
Ah, so this is where I can finally block that one bad actor.
Exactly. If you have a specific IP block attacking you, or you want to block traffic from an entire specific country, you do it at the NACL level. You stop the malicious traffic at the border before it even touches your expensive servers.
I see. So you use the NACL for the big sledgehammer blocks and use security groups for the fine-tuning at the door.
Correct.
Now let's zoom out a bit. We've built one very secure fortress, but companies rarely have just one. Say I buy another company or I have a dev environment and a broad environment. I need them to talk to each other.
Then you are looking at VPC peering. This feature allows you to connect two different VPCs, so they essentially behave like one network.
Nice.
And the beauty is the traffic stays on the AWS private backbone. It never touches the public internet.
But there is a catch here, right? And it involved those IP addresses we talked about at the very beginning.
The overlapping CIDR problem. Yes, this brings us right back to our foundation. You cannot peer two VPCs if they have the same exact address range.
So if both my prod VPC and my newly acquired company's VPC were set up as 10.0.0.016,
Peering fails. It is mathematically impossible. It's like trying to merge two cities where all the houses have identical street addresses.
the postman just creates a black hole.
Exactly.
Yeah.
The routers literally don't know where to send the packets.
This is why that initial planning is so vital. If every single team in a company builds their VPC using the default settings, or they all follow the exact same blog post tutorial, nobody can ever talk to anyone later.
Exactly. And even if they do have different IPs, what if you have 50 VPCs? Peering them all to each other creates a nightmare we call the peering mesh, or just spaghetti architecture.
Unmanageable.
Completely unmanageable. You have hundreds of point-to-point connections to maintain.
So what is the fix for the spaghetti mess? There has to be a better way.
There is the transit gateway. Think of it as a regional virtual router, a massive central hub.
A hub and spoke model.
Right. You plug all your VPCs and even your on-premises data center VPNs into this one central hub. It handles all the complex routing between them. It is infinitely cleaner, but again, it is another component you have to manage and pay for.
Speaking of the global network, I saw a stat in the documentation about the AWS private global network that frankly blew my mind.
Oh, the packet loss rate.
Yes.
It is deeply impressive. AWS aims for a packet loss rate of less than 0.0001% on their global backbone.
That is absurdly low.
It is. When your traffic moves between AWS regions, say sending a database replica from Tokyo to Virginia, it doesn't bounce around the chaotic public internet. It stays entirely on AWS's private, custom-built fiber backbone.
So you really are paying for reliability and performance at that scale.
You definitely are.
Which actually brings us to the topic everyone loves to hate, cost. We already mentioned the NAT gateway toll road, but I saw a major pricing update recently regarding public IPv4 addresses.
This is huge. For years, getting a public IP address on AWS was basically free as long as you were actually using it. But globally, we have simply run out of IPv4 addresses. They are a genuinely scarce resource now.
Supply and demand kicks in.
Exactly. So AWS has started charging an hourly rate for every single public IPv4 address you allocate, whether it is attached to a running server or just sitting idle.
So if I have a dev environment with 50 servers, and I lazily gaze them all public IPs just because I didn't want to bother setting up a NAT gateway,
You are now paying an hourly tax on every single one of those 50 IPs. It adds up to hundreds of extra dollars a month for larger environments.
that is a massive shift in behavior. It basically forces you to stop being lazy with public IPs.
Ideally, yes, it forces you to use private subnets and NAT gateways. But as we discussed earlier, NAT gateways cost money too.
There really is no free lunch in the cloud, is there?
No, just a menu with very complicated pricing.
Okay, let's wrap this up. We have covered a massive amount of ground today. We went from the initial digital plot of land to the complex physics of stateful versus stateless security, all the way to the literal cost of an IP address.
It is a lot to take in. But if the listeners take one core thing away from all this documentation, it should be this. The cloud is not just someone else's computer. It is a fully software-defined environment.
Right.
Features like security group referencing allow you to build networks based on identity and logic, not just physical cables and hardware ports.
It's networking with a brain.
Exactly. And because it's software, mistakes in the foundation, like that CIDR block size, are much, much harder to fix later than simply moving a network cable.
Measure twice, cut once.
Exactly.
Well, here's a final thought I want to leave everyone with. We spent a lot of time today on the stateful nature of security groups. You know how they magically handle the return traffic versus the stateless amnesia of NACLs?
Yeah.
If the stateful way is so much smarter and easier and generally safer, why do we still cling to stateless protocols in other parts of technology? Is the future of tech entirely stateful, or is there actually a hidden value in having amnesia?
That is a surprisingly deep philosophical question for a networking show. I mean, maybe sometimes it's better not to remember everything.
Something for you to mull over while you audit your route tables and carefully check your NAT gateway bill. Thanks for joining us on this deep dive.
Always a pleasure.
See you next time.